Hello there, and welcome back to our lecture series here. Up on top for today is chapter 14. We're going to talk about solutions. We're going to talk about some properties of solutions. We'll also talk about concentration units. And at the end, we'll talk about colligative properties. It is going to be a 3-part lecture series. This is part 1 of solutions. Professor, start the lecture. All right, everybody, it is chapter 14 up today. Dare I say, we are approaching the finish line here. I think we got just one more to go after this chapter, so that's good for the semester. All right, chapter 14, a lot going on in chapter 14. It is solutions time. So we're going to talk first off about solutions, some properties of solutions, how they interact with each other. We'll talk about how to make a solution. We'll also talk about important concentration units for solutions. And we'll finish up this chapter with a little bit of stoichiometry, of course. Why not throw it in for free? And we'll talk specifically about different types of solutions and properties of solutions, of how they interact in terms of osmotic pressure, colligative properties. So we'll cover a little bit about some colligative properties at the end of this chapter. So let's get into solutions. Once again, a reminder, which I think we've talked about in some previous chapters. Solutions really, again, are homogeneous mixtures. And remember that these are the guys that when you look at formulas will typically have that aqueous symbol next to it. Implies that something is sort of dissolved in it and is not just a pure substance. And again, that's why it's really a mixture. And as we'll talk about the two important parts to a solution, again, we'll kind of preview it here, or we might have talked about it previously, is the solute and the solvent. And again, if you had something like, say, sodium chloride, a sodium chloride solution, that would be really a mixture of water, which is the solvent, the larger part of the solution. And the sodium chloride here would be what is known as the solute. And once again, both of those things together is what makes a solution. So obviously, if you took some salt and dissolved in water, it's going to dissolve no problem. And again, you would have an aqueous solution that is a homogeneous mixture. A reminder that a homogeneous mixture, right, is looking the same throughout, right? So typically these things will be soluble in each other, and one will dissolve in another. So let's talk a little bit about how liquids and liquids mix together. When we do have two liquids, sometimes we don't use the word soluble and insoluble. A lot of times we will use those words, as we will talk about here as well, and we do use it in terms of liquids and liquids. But sometimes we will use two other words when we're kind of dealing with liquids, kind of mixing with other liquids. So typically things are soluble. That's also sometimes referred to as being miscible, especially when we're talking about two liquids together. And something's insoluble, which means they kind of really don't mix. That is usually immiscible. So those are kind of two other words that are sometimes used for solubility, especially with liquids and sort of liquids mixing together. So when we have two liquids that completely mix together with one another, they are said to be miscible in each other. And again, what that would really look like, when you would put those two solutions together is sort of like this drawing. So if we took something like the example there, which is ethanol and water. And once again, ethanol and water are able to interact well with each other through what we talked about when we were talking about those intermolecular forces. So just a quick sketch here of ethanol, and I think we might see it on another slide coming up, but why not? I'm halfway through ethanol's drawing, so might as well finish it here. And something like water, for example, here. Remember that although ethanol here has a non-polar part, it does contain this part right here, or this bond, which is a polar bond. And that means that this side is going to be more negative, the oxygen, the hydrogen is going to be more positive. Remember that water is also polar, contains really the same exact bond. And again, the oxygen side being more negative, the hydrogen side being more positive. This allows these two guys to interact really well with each other through what we were talking about previously, which is that hydrogen bonding action right there. So a little hydrogen bonding action. And remember that that's going to make them really soluble together. So a really important thing about solubility, as we might have talked about previously, and we'll definitely talk about a little bit more here in this chapter, is the idea that things that have similar ways of interacting with themselves through their same type of intermolecular forces, they can interact with other molecules that have a similar intermolecular force. So that makes things really, really soluble in each other. Now, if we do have two liquids, for example, that are not going to mix really well, we have something that's immiscible. And when they're immiscible, you really will see when you're mixing two solutions or two liquids together, you'll really see these different layers that will happen. And it's really because they will not mix together. So example here, carbon tetrachloride with water is going to be immiscible in water or insoluble in water. And that's because when you just quickly, once again, sketch out carbon tetrachloride, once again, although it may contain polar bonds, or it may not contain polar bonds, as it may have sort of that diagonal relationship, but in this case, it does actually contain some polar bonds. But the geometry here is symmetrical. And that means that all those polar bonds are going to cancel each other out. And this is going to be a non-polar molecule, which now when it tries to interact with water, which once again is a polar molecule, we run into that trouble that we talked about when we were talking about intermolecular forces. We have water, which pretty much as it rolls through with itself or anybody else, is pretty much looking to interact through hydrogen bonding. Now, when we have non-polar guys, if you remember, they pretty much roll with dispersion forces, which are those really weak intermolecular forces. Thus, we have very different modes of interacting with themselves, which means when they come together, they're going to have a really hard time and struggle with interacting well with each other. They typically will not, because of that very difference in the way that they use intermolecular forces. So remember that although everything can, in a sense, polar molecules, non-polar molecules, use dispersion forces to an extent, it is not a very strong interaction and is not really the main intermolecular force as something like water uses. Water mainly uses hydrogen bonding. So they can't maintain that interaction. You're going to get that layering that's going to happen. You're going to see these distinct phases that we do not see when something's miscible. This brings up, again, a super common saying when we talk about solubility, both just regular solubility and solubility in liquids. And that's the idea that like dissolves like. So that's basically the idea, as I just mentioned here, and I think previously as well, that once again, things tend to be soluble when they interact with other molecules that have the same type of interaction that they do with themselves. So the way that they sort of roll with themselves, and if somebody else can roll the same way in terms of their intermolecular forces, they're good to go. And if two are using different or completely different types of intermolecular forces, that is where things are not so good. So when we talk about like dissolves like, and we talk about things being soluble or miscible in each other, in general, if you have something that's ionic and something that's polar, that's going to be all good to go. That's going to use that ion dipole interaction we talked about with intermolecular forces. Something that's polar and polar, once again, are going to be fine, because either they're going to use hydrogen bonding and hydrogen bonding, or they're going to frankly use dipole dipole and dipole dipole, which is kind of very similar to each other, and they'll be fine. The one sort of interaction that sometimes people overlook when they kind of go through, you know, what types of interactions are soluble with each other is the nonpolar and the nonpolar. Those guys, remember, also will be soluble in each other because they are both using dispersion forces. So they also will be soluble in each other. For the most part, you're going to run into some trouble or some insolubility, if you will, kind of when you cross over that line between trying to take something that is polar and something that is non-polar. So at that point, you once again, which is pretty much what we have in this situation, you're going to run into a situation where they are not going to be soluble with each other. So like dissolves like is a good thing to keep in mind. And again, ultimately, as we've talked about in a few different points along the way here, it is those intermolecular forces that play a really tremendous role in terms of solubility and how things mix with one another. So here's a picture once again of those things. And here we see definitely some layering out that's happening here. So we got some insolubility happening. And over here, you know, we also actually see some different layering happening as well. Although this guy over here could be on his way to being completely purple all the way through, even though I just drew a green there. And that could be something like potassium permanganate dissolving in water. But definitely over here, we do see some different layering happening. So let's talk about some solubility of things in water. Once again, as I mentioned before, ionic substances are typically soluble in water, and that is that ion dipole interaction like we talked about with water. Once again, when we try to dissolve an ionic compound in water, what happens is that negative side of water, which is the oxygen, once again, will surround that positive side of the, or I guess the only side of it, the positive ion in that case. And again, that is where that interaction happens to help it dissolve. Once again, the chloride ion, or the negative ion, we won't just use chloride, but the negative ion here, we get an eraser. Just use a generic negative ion. Will also be surrounded by water, but once again, it'll be surrounded by that positive side of water. And again, as we talked about, this is pretty much how things dissolve, but you can't really see it. And again, that interaction is going to happen there, and they're going to dissolve. Now, there's also non-ionic substances that are definitely very soluble in water, things like sugar, things like ethanol. So as we just talked about a second ago, something like ethanol has the ability to hydrogen bond. So that is why it is very soluble in water. But what about sugar? Well, sugar is a little bit of a larger molecule, but we'll see a picture of it, I think, coming up. But sugar pretty much has a ton of these OH groups. So it's got a bunch of OH groups all over it. And everywhere there's an OH group, it gives it the ability to hydrogen bond and also be very soluble in water, and gives water a place to interact. So one way sugar, which is a little bit larger than some molecules, are able to interact well with water is because of the presence of those OH groups. And one thing about solubility and increasing solubility is if you have a molecule that has a lot of OH groups, pretty much as you increase the number of OH groups on something, it gives it more places, as I just mentioned, to hydrogen bond and interact with water. It also very much so increases the solubility of that substance. So if you're comparing, say, a compound that has only one OH group with maybe a one that has 2 or 3 OH groups, the one that has 2 or 3 OH groups definitely will be more soluble than the one with just one. So covalent bonding here, once again, this is methanol down here. If I found my pin there, that's methanol right here, and our methyl alcohol. And once again here, this is the OH group on methanol, which again is positive, negative, and our water, which is negative and positive. And we even have one over here, negative and positive. Again, giving it multiple places to hydrogen bond with multiple waters, and that makes it very, very soluble. Here's the ethanol example that I drew earlier. Again, the ability to hydrogen bond, going to make it really soluble. Remember that we also talked about the idea that, and I think I might have drew one in that chapter we talked about with intermolecular forces. I don't even know how many carbons I drew on that thing, 9 or 8 or something like that. But solubility does start to decrease once again, just as a subtle reminder that if you really increase the non-polar side, say, of these molecules, which are really organic type molecules, the solubility starts to really, really drop once you add a lot more carbons and hydrogens. So Remember that this part of it again is non-polar. So as you continue to add really just more carbons and hydrogens, carbons and hydrogens, carbons and hydrogens, carbons and hydrogens all the way across, what you're doing once again is creating the side of this molecule that is really large and also non-polar. So it prevents really water from getting in there to interact well. And as I might have mentioned in that sort of intermolecular forces lecture, when you have something that dissolves in water, as we will talk about here on this slide, what you essentially need to do is kind of create a hole between water molecules to insert whatever you want to dissolve. So you have to remember that, you know, before you throw anything into water to dissolve it, you pretty much have a network of water molecules, right, that are bound to each other. And, you know, got all these water molecules that are interacting with each other. And once again, in order to get something to dissolve, you got to kind of take some water out and kind of put whatever you want in to dissolve. And when you get something like I was just describing, where you sort of add a bunch of those carbons and hydrogens and increase the non-polar part of that molecule, or you just have something that's straight up non-polar, that is problematic because it has no way to interact well with it. Even if it happens to have that OH group, there's that steric hindrance issue where it's just too hard to get in there because of the overall size of that molecule. And you also have something that's too big to mix really well. So water is a small molecule, and when you try to put something really large in there to get it to dissolve, even it may have the ability to interact, just that non-polar part that's really, really large gets in the way. So I might have used this example earlier, but once again, you could think of it just logically about sort of like a garage. If you're going to park a car in a garage, you know, you could put a car in there, it's okay. You put a slightly larger car in there, maybe like an SUV, and it might fit okay. But if you try to put like a semi-truck in there, you get part of the semi-truck in, but it's just not going to be right the way it's going to interact with your garage. It's going to be hanging out, right? It's not going to really sort of mix. And it's sort of the same way when you have something that's really large and non-polar and you try to have it interact with water, or something that's really large and even has a small polar part like an OH group, it's not going to interact really well. And that's also why when we try to dissolve, say, something or mix something like oil and water, they definitely do not mix. And that is because oil is basically made up of nothing more than, and I'm not going to draw a ton of these, but maybe I'll draw a good amount. Pretty much oil is just a non-repeating pattern like I'm drawing here, and it just goes on from one side and the other, just kind of keeps following this pattern. Just a really long carbon to carbon chain, which is definitely a non-polar bond. Also long carbons and hydrogens bound to each other, which is also non-polar. So you got this big old molecule, which is basically like oil. And by the way, it just continues on both sides. And it's non-polar. And it's going to be rolling with, once again, dispersion forces. We got our water here up here. It's going to be rolling with hydrogen bonding. Not going to work really well. Once again, also pretty big guy, not going to mix really well with it at all. And that's what we usually see with water and oil, right? Is actually, once again, here you get that oil that kind of floats on top of the water. That happens. So that brings up again that idea of like dissolves like, things with similar intermolecular forces, good to go. They're going to interact really well. Things with very different intermolecular forces are not going to interact well. And once again, the one thing that you do need to think about is, even though something may be able to interact well or the same way as, say, with water, the size of it and is there a non-polar part, it's also really, really important. So something like that OH group and a bunch of carbons. I might have mentioned in the intermolecular forces chapter that you know, usually if you're about 5 or less carbons with the one OH group, you're going to be fairly soluble in water. But once you get about over 5, 6, 7, 8, 9 or more sort of carbons that has that one OH group, solubility again drops to nothing. And once again, if this wasn't oil, for example, but was something that had that OH just kind of still in the drawing here, again, this would be way too many carbons for this OH group to interact. Even though it's still polar, it still technically has the ability to work well with water, but this part back here, too big, too non-polar, not going to work well with water. And that brings up a couple of different types of interactions. Hydrophilic interaction is basically water loving, and that is any polar region on a molecule that will basically be able to interact well with water. They typically will have OH groups like in ethanol, and that's going to make it water loving because it could hydrogen bond with water, so it'll be very soluble. Hydrophobic is actually water hating, and those are really non-polar size, say, of hydrocarbons, which is like those organic things we were just talking about a second ago with all the carbons and hydrogens, are something like in ethanol, that carbon hydrogen part of it. A place where we actually see, and again, I might have mentioned this during that intermolecular chapter, but if not, let me mention it now. Something that we use every day that kind of does both of these things, or actually has both of these types of regions, is something like soap. Soap is basically made out of a really long chain carbon and hydrogen part. And once again, I'm not going to draw all of them. Sometimes it's almost like 18 or more carbons and hydrogens. So I'll just put some dots going this way. So we have this really long carbon and hydrogen part of soap. And just kind of fill it in here. And this clearly, as we've been talking about with those previous slide there, this part of it is really non-polar. And it is sometimes referred to as, in the case of soap, the non-polar tail of soap. Now, at the other end of soap, you have typically this type of group that is present. And this is also an organic group. And this is what's known as a carboxylic acid group. And typically with soap, though, you do not have the hydrogen there, which really makes it a carboxylic acid. So you have this hydrogen missing, and you typically will have a negative charge here. But essentially, this is a polar group. This is what's known as a carbonyl group, and this is actually polar, negative and positive. Over here is negative. And this part of soap is what is referred to as the polar part of soap, and sometimes referred to as the polar head of soap. So this is essentially what soap looks like. Now, speaking of like dissolves like and how soap works, it has these two parts, and these two parts are hydrophilic and hydrophobic. So why don't you take a second and decide which part is which in this case. So just take a second and decide where you would think would be the hydrophilic part that likes water and which part does not like water. All right, so non-polar, right, is water's polar, so that's going to be the hydrophobic part. This is the part that does not like water. The polar part, and water's polar, is the hydrophilic part. That is the part that likes water. So why is this important? Well, in case you're not sure of, if you have dirt, dirt is essentially, in most cases, non-polar. And what that means is when you put soap to, say, wash your hands or whatever it may be, the non-polar part here, this non-polar tail of soap, is going to be attracted to the dirt, which is also non-polar. Once again, like dissolves like. So what I'm going to do, instead of drawing all those carbons and hydrogens, I'm just going to represent these carbons and hydrogens as this kind of mountain zigzag range. So what happens is the carbon and hydrogen part of soap will basically attach itself, and we're just going to draw a few of them here, to dirt and basically surround dirt. And what it will do is it will align itself that the outside part of soap will be on the outside of the dirt, basically. This is what is sometimes referred to as creating a micelle. So basically the non-polar side, we'll add one here for good measure. The non-polar side of soap will basically surround all the non-polar dirt. And what happens is, once again, it aligns that hydrophilic or water-loving side on the outside, right? So we have all this water-loving part of soap basically on the outside. That's really good because, if memory serves me correctly, after you put soap on your hands, you usually like wash it off with water, which is good. So now when you do that, you're throwing a bunch of water there on the outside here. It has access to the outside part of all these soap molecules. And that's good because the outside part of soap is attracted to water, basically, right? And now we can have our hydrogen bonding sort of happening here with all those water molecules. And the outside part of soap will then be very soluble in water. And what that does, right, is when you wash off your soap, because now the outside part's on the outside there and soluble with water, it will take everything with it, and off goes your dirt, and your hands are clean in that case. So soap's an interesting molecule. It actually has both parts to it, a hydrophobic part, a hydrophilic part, a nonpolar part, and a polar part. And it actually, both parts work really well for its function. And again, its function there is to grab up all the dirt and trap it, align all the soap molecules on the outside where only the outside part is attracted to water. You wash it and there goes all your dirt with it. And again, taking advantage of the properties here of both the hydrophilic part and the hydrophobic part works really well. So that's just a little side note of how soap works. Everybody should know, I suppose, how soap works. It's a good life lesson, I suppose, in case it comes up in conversation. I don't know what type of conversations you're having. Maybe you have conversations on soap. Who knows? Here's a couple other examples of things being miscible and immiscible here, are insoluble. Here's a potassium permanganate crystal. Makes this really pretty purple color. Don't get it on you if you ever use it. Turns everything purple, but will dissolve in water. And once again, potassium permanganate, one of those polyatomic ions we talked about, is really a potassium ion and a permanganate ion floating around. And once again, they're going to be able to be surrounded by our polar water all the way around. And again, I'm not going to draw all the waters, but they're going to be able to interact here. And once again, doing ion dipole interaction, and now they're going to be very, very soluble. Here's our oil and water. Once again, the oil coming in, as you can see here, temporarily could do a little bit of mixing as it is trying to use dispersion forces. But once again, our water here, it wants to use hydrogen bonding, and ultimately what's going to happen is we're going to get some different layering, and our oil is going to separate out there. So solubility, when one substance, once again, is soluble, the solute, it dissolves in another, which is the solvent. It's said to be soluble. Salt is soluble in water. When one substance does not dissolve in another, they're said to be insoluble. Oil is insoluble in water. There is a limit to the solubility of one substance in another. Gases are always soluble in each other, and that's because gases are basically always flying around, which means they are constantly mixing as a result of that. Some liquids are also mutually soluble. Again, polar and polar liquids. Non-polar and non-polar liquids will be soluble in each other. Once again, if something is soluble in each other, typically that will lead to a solution. As our example earlier, as I mentioned, something like sodium chloride and something like water are going to be soluble in each other. This, once again, is our solvent, which is the larger part of the solution. And here, sodium chloride would be our solute, which is the smaller part of the solution. And once again, when they do dissolve, our sodium chloride dissolves into the solvent there, liquid, we do get that sodium chloride solution. That is aqueous, which we sort of talked about when we talked about solubility rules, right? Things that are aqueous in each other, we'll get that AQ sign, are soluble in each other, we'll get that AQ sign. Things that are insoluble in each other, right, when we talk about sort of those solubility rules, are going to be solids. Just a refresher here, some of our solubility rules that we talked about in that previous chapter when we did double displacement reactions, precipitation reactions. Here are things that are soluble, right? And remember that certain things have exceptions. So all these guys should be aqueous all the way through. And all these guys are insoluble, which means anybody that is this combination would be solids that would get it. So once again, if we took our sodium chloride and we reacted with our silver nitrate, once again, this is going to be a double displacement reaction, right? Positive, negative. Positive guys are going to switch partners. And that would give us some sodium nitrate. Remember that sodium is +1. Nitrate is -1, which means when you put them together, that is the correct formula for sodium nitrate. Silver is +1. Chloride is -1, which means when you put them together, that is also the right formula. We could use our solubility rules here to determine what everything should be. I see sodium, which is right here. There's no exceptions, so I know that this is going to be aqueous. I see nitrate here, which is also here with no exceptions. I know that this is going to be aqueous. I see sodium here, no exceptions, going to be aqueous. I know this is going to be soluble as well. I see chloride here, which does have some exceptions, and one of the exceptions is silver, which means it is going to be solid. So once again, that would be a precipitation reaction. So our solubility rules helps us decide whether or not something ionically will be soluble in water. And again, we saw these rules and did a number of these things when we were talking about that section 15.6, I think, lecture, somewhere in there, when we talk about double displacement reactions in that chemical reactions chapter. Now, again, talking about solutions and solubilities, molecules that are similar structure tend to form solutions. And again, that like dissolves like. The solubility of a solvent, which is the larger part of a solution, depends on its temperature. Typically, at a higher temperature, you could have a larger solubility of a solid and liquid. So sometimes when things do not dissolve, or you take a solid and you want to dissolve it in a solvent, or we take a solute solid there to dissolve in a solvent like water, and you can't get it to dissolve, a lot of times if you heat it up, it will actually typically increase the solubility of a solid in a liquid. Vice versa as well. If you lower the temperature, typically that will decrease the solubility of a solid in a liquid. Why is that? Well, if you increase the temperature, there's more energy. That's going to allow a lot more water molecules to move faster, more energy as the solid is trying to dissolve. It'll just allow the dissolving process to occur a lot easier. When you lower the temperature, you're removing a lot of energy, which means your water molecules aren't moving as much. And also that solid is just not losing more energy and going to kind of lock into place and become more and more solid and less soluble, which means it will not dissolve. Also, what happens in some cases with lower temperatures is you have a larger solubility of a gas in a liquid. And why would that be? Well, kind of the same reason. At a lower temperature, if this is my gas molecule that's dissolved in the liquid part, it's going to be moving slower. Dramatic drawing there as it's moving slower, which means as it tries to move its way through the liquid part, maybe to escape there, it is going to stay in the liquid part for a lot longer because it's not moving as fast. Vice versa would be true as well. If you increase the temperature, your gas molecule is going to move a lot faster and probably be able to escape a lot faster, so it'd be less of it dissolved. Also, solubility of gases does depend on pressure, so typically the higher the pressure, the larger the solubility of gases are. And that goes back to sort of Boyle's law, right? As pressure goes up, volume goes down. So once again, if we had a large pressure, that is because in this smaller volume, we have a lot more gas molecules near each other than in a lower pressure, a larger volume. we have a lot more room for everybody to spread out. So they're not going to come in contact with each other or mix as much as they are in that sort of higher pressure. Here is again the process of dissolving. This is what an ionic solid looks like before you dissolve it. And again, these are your like negative ions. The smaller guys are your positive ions. So again, they're sort of aligned in a really nice three-dimensional sort of process here, organized situation and ordered pattern. When you go to dissolve it with water molecules, as we talked about, there's just so many water molecules in there. They're able to, as you can see here, kind of pluck off the ions. Once again, you help this by, you know, taking something like a stirring rod, right, and start mixing, right? And as you mix it, you're throwing a lot more water molecules over the surface of that solid. You're also, again, providing a little bit more energy, which is going to allow everything to dissolve a lot easier. So how do we describe solutions? Well, there's a couple of ways we can describe solutions, but there is a limit to how much solute you can dissolve at a given amount of solvent. And that limit is temperature dependent. So again, temperature plays a big role as to how much solid you can actually get to dissolve in a solvent. So what happens when you have too much of the solute dissolved? And again, the solute is the smaller part of the solution. The solvent is the larger part of the solution. You get what is referred to as a saturated solution. And a saturated solution is basically at that particular temperature, you've reached the maximum amount of solid that you could get to dissolve in that solvent. You pretty much hit what is sometimes referred to as the saturation point. Boom, you're there. And what that means is you're at the point where exactly if you were to try to dissolve any more solid, good luck with that. It's not going to happen. So what will happen is it's going to basically just start piling up on the bottom. And that's a saturated solution. So you can think of it like, you know, if you take Costco size sugar that you bought and you dump it into a glass of water, at some point you could stir all day. You have way too much sugar to try to dissolve, say, in a glass of water. If you just keep dumping the sugar in and so forth, it's just going to pile up on the bottom. What is the opposite situation? Well, the opposite situation is you're not pretty much there yet. You're in what we call an unsaturated solution. And an unsaturated solution, you have not hit that really saturation point, that maximum amount of solute that will dissolve at that given temperature. That means that if you are at that point and you continue to add more solid to it, it will continue to dissolve. How far will it dissolve? Well, it will continue to dissolve until you hit a saturated solution. So let's say you didn't take the Costco size sugar, but you had a glass of water and you took like the little sugar packets that you find say at a restaurant or something like that, and you put that sugar into your water. Definitely you dissolve it, boom, gonna dissolve, not a problem. So maybe you can put another sugar packet in there. You dissolve it, not a problem. Again, maybe you got a lot of sugar on your table there and you can keep opening up those little sugar packets and dissolving it. Again, at some point, you will reach this saturated solution where no more of that sugar will dissolve. And then you really have a saturated solution at that point. Speaking about that, here's a couple of tables from your book. And again, the differences here between temperatures. So for example, that's 0 degrees Celsius. That's 100 degrees Celsius. So that's obviously a lower temp. And that is a higher temperature. And what we're looking at here is how many grams of each of these ionic compounds that we could dissolve in 100 grams of water. So just comparison from the left-hand column to the right-hand column for each of these things, what we see is what we were just talking about. As the temperature increases, so does the solubility. So for example, lithium fluoride, you can get 0.12 grams at 0 degrees, not much higher, but you can get 0.14 grams at 100 degrees. Lithium chloride, 63 grams, and it goes up to 127 grams at 100. We'll look at our sodium chloride here, 35.7 grams at 0 degrees and 39.8 grams at 100 degrees. So this is the same amount of water in each case, and that means that we could dissolve each of those things. Our sodium bromide, for example, 79.5 and 121 grams at 100. So let's say let's say we are at 100 degrees Celsius. Could I dissolve? I don't know. Could I dissolve? We'll go with 36,500 grams of, we'll go with sodium bromide. And we'll go with 250 grams of water. All right, so use this chart. We're about here, I think, and see what you come up with. Decide, could I dissolve it in that many grams of sodium bromide in 250 grams of water at 100 degrees? So take a moment and see what you come up with. Okay, so let's see. How could we use this information? Well, we could use this really as a conversion factor. So we're looking at sodium bromide. And we got 121 in 100 grams of water. So basically what that means is at 100 degrees Celsius, we have basically two conversion factors. We could get 121 grams of sodium bromide to dissolve in 100 grams of water. We could use it like a conversion factor, which means we could flip it around. 100 grams of water, we could toss in there our favorite 121 grams of it. So what we know is we do have 250 grams of water. So if we just do a little dimensional analysis here, 250 grams of water. We want opposites to cancel. So grams of water on the bottom, which means this guy. 121 grams of sodium bromide, 100 grams of water, cancel. And that's going to give me here, if I grab my calculator, looks like 30,250 grams of sodium bromide. That means based on this table and the solubility of sodium bromide at 100 degrees Celsius, if I had 250 grams of water, that is as much as I could dissolve. So the question here is, could we dissolve that much? The answer is no, you could not. That means that if you tried to do that, if our only two choices of types of solution is unsaturated or saturated, at this point, we are definitely in the saturated would be the better choice, because we're trying to definitely go way over 30,000 grams. So at some point, you're going to have about roughly, I don't know, 625 grams of sodium bromide that's not going to dissolve at this temperature. Where's that going to end up? Well, it's going to end up at the bottom of your beaker, wherever you're trying to dissolve this. So definitely hit the saturation point and then some at this point. And that is sort of how you could use this. All right, let's take a look. Here's another table. This is actually between 20 degrees and 50 degrees. Same thing. How much grams of these guys we could get dissolved. Let's just do, we'll do potassium chloride. Why not? All right, so let's just say, let me see here, potassium chloride. Could I dissolve at 20 degrees Celsius? We'll go with 19,555, why not, grams of potassium chloride in, I don't know, let's do 625 grams of water. That's maybe what I want to do there. All right, take a moment, use the information here and decide, could I dissolve in this one? And out of our two choices, which one would best describe this solution? Is it a unsaturated solution or is it a saturated solution? Which two of these guys or which one of those two would be the best? All right, take a moment, see what you come up with here. All right, let's take a look, see how you're doing. So once again, we're going to use 20 degrees, which is right there. We're going to use this as a conversion factor. So once again, what that means from this table, that is how many grams of our solute, which is our stuff we're dissolving, in 100 grams of water. So that basically means I have 34 grams of potassium chloride in this case. I could get to dissolve in 100 grams of water. Once again, we can use it as a conversion factor, 100 grams of water up on top, and 34 grams of potassium chloride. So once again, in this case, probably one of the easiest way to do it is that we know how much water we want to dissolve it in. So we'll take 625, if I put the 2 in the middle there, 625 grams of water. Using this is going to allow us to figure out really the solubility of potassium chloride in water, this much water at 20 degrees Celsius. So this number that I am getting here, water will cancel, tells me that basically I take 625 times 34 here. Going to give us about 21,250 grams of KCl. This number once again reflects how much of this salt, our ionic compound, KCl, we could dissolve at 20 degrees Celsius in 625 grams of water. So we could dissolve 21,000 grams. We are only shooting to dissolve 19,555 grams. This should not be a problem. Yes, we should be able to dissolve this because we got plenty more to go. We got over, I don't know, there's a lot of them out there involved there, but I don't know, 1,800 grams or so to go. So yes, and because we still have some more grams we could dissolve at this temperature with this amount of water, this definitely would be a unsaturated solution at this point. So this is, again, a practical sort of calculation that will help you determine, obviously, is something going to be more of an unsaturated solution or saturated? Could you dissolve this much in it? And just the front part of this calculation, regardless of the question, is basically telling us how much at that given temperature in that much water we could actually get to dissolve. So there's a lot of pieces of information you get here. You do need to know how to do these type of calculations and figure these type of things out. All right, so let's talk about one other way to classify a solution, and this is what is sometimes referred to as a super saturated solution, because it's super and it's saturated. So super saturated solution here. So what is a super saturated solution? Well, a super saturated solution is, technically speaking, a solution that for a certain reason pretty much has too much solute. Which again is the smaller part of the solution, usually the solid you're dissolving, has too much of that solute dissolved in a given amount of solvent. So how would you make, say, a supersaturated solution? Well, one way that you would make it is, for example, sodium acetate is a very common example of this. You take some, say, sodium acetate and you kind of heat it up and you start dissolving some sodium acetate in here. I'm going to make my sodium acetate solution purple. And it is not, by the way, but since I have purple on my pen here, we'll make it that. And you're going to get this solid to dissolve in the water to make this sodium acetate solution. We are doing a couple things here. We're heating it up. So as we just talked about, that is going to increase the solubility of that, say, solid sodium acetate crystals in the water, right? Because we're increasing the temperature, going to increase the solubility of it. So we'll get all that guy to dissolve a lot because it's hot, basically. So typically, if we did that, we get all this solid to dissolve in the solvent. By the way, when you're heating it up, perhaps you're going to lose some of that solvent water through evaporation, right? Because you're heating it up. Then what you would typically do is take that, say, test tube that you may have at this point, and I won't color it in purple at this point. It would be colorless at this point. And you will cool it back down, undisturbed. And that's a really important part. because you do not want to disturb this. And that's because when you have a super saturated solution, it becomes a really unstable solution, because you have now, as you are cooling this back down, the solubility of what's dissolved in there is going to decrease. But at this particular point, it's a little too late, because you've already dissolved the solid in there. So you have now like increased the temperature, get all this solid to dissolve. Then you lower the temperature back down without disturbing it, and you're going to have now dissolved in this solution way too much solid for that temperature that the solution has now dropped back down to. It creates a super unstable solution at this point. It is so unstable that, and I've done this before, this demonstration here, if you actually just kind of touch it or move it too hard, or put the test tube back in the rack too hard, or if it's in a flask, put the flask down too hard, it will cause all of that solid to decide, wait a sec, all that solute, which is the solvent, decide I should not be dissolved in here. And you could do this by accidentally knocking it too hard because it's so unstable. But a lot of times you could actually have this happen by just taking, I'll just try to do it on the screen as best I can, like one super small crystal of whatever you dissolved in there. And if you just drop that one little tiny crystal into here, what you will see is they'll go, no, thank you. Too much. It's like the straw that broke the camel's back there. It's like that is the tipping point. And before you know it, all of that solid that's in there will start to come out of solution, and it will go from the liquid state, and the test tube apparently will get bigger, and it will go now, and this thing will be rock hard solid in there, and it'll be completely solid at that point. And that's because it is a really unstable solution, that one little bit of crystal is enough to push it over the edge, that it recognizes at that point, whoa, this is not the right temperature for all that's dissolved in there. You should not be dissolved in here. For lack of a better description, it like kicks out all the solid from the actual solution part, and it goes from being a liquid solution to a solid solution. It's a very common experiment a lot of schools used to do. We don't do it here anymore, I think. But here is in this picture, our super saturated solution of sodium acetate. And it is a solution at this point, liquid. And you can barely see it, but right there, they took one little crystal and dropped it in there. And you could see as soon as it hit, let me actually get a different color here. As soon as that thing hits right there, you could actually start to see the solid like starting to come out. And as it goes in, boom, and hits in the center, that is all of the solid starting to come out of the solution. As you can see, it gets bigger and bigger and bigger until essentially this entire thing will now be completely solid at this point, where it started as a liquid back over here. And that is because that is a super saturated solution. It's a cool experiment. And it's just a solution that just at a particular temperature it is currently at has way too much solid or solute dissolved in there for it to keep dissolved. So definitely limits the solubility, definitely temperature dependent on how much solute you can get to dissolve in a solvent. I'll talk about some other aspects of solubility and a little bit about gases. Pressure and solubility of gases. External pressure has an effect on the solubility of gases. There's actually a gas law, which you don't really have to worry too much about. I don't think it's actually specifically mentioned in your book, but this is Henry's law. And it says that the solubility of a gas is proportional to the pressure of the gas over liquid. And this is Henry's law, two versions of it. This is concentration, which is typically molarity, which we'll talk about in this chapter. This is actually a constant that you can look up in a table for the actual gas that you're going to look are used. And then P is pressure here. And same thing here. This is sometimes what is referred to as S is the molar solubility, which, as we might talk a little bit about, is essentially still molarity at that point. So what is the idea behind sort of Henry's law? It's kind of the soda can example. And what I mean by that is when you have a soda can, such as this, before you pop the top, you have a lot of gas, CO2, that's dissolved in the liquid part. So you can see a lot of the gas molecules here, the CO2 molecules. Because of that high pressure, you can keep the volume of those gas molecules low, and that's going to keep most of those CO2 molecules dissolved in the liquid part of your soda. When you pop the top, you sometimes see this happening, right? A little fizz coming out the top, right? That's like your CO2 gas escaping. And you also release the pressure, right? A lot of pressure released in that case. And that's also going to give those gas molecules an escape route, right? Also, by the way, why your soda can goes flat after a while, because as those CO2 molecules escape, air blows them away, which means air cannot go back into the liquid part of your soda. So when you grab your soda can after it's been out for a bit, it tastes flat because all the CO2 molecules with all that less pressure and also an escape route up there on top leaves your soda part, and now you got basically just flat water, not carbonated water basically, and flavoring obviously, and it tastes very, very flat to you. Just to give you an idea in terms of a soda can, for example, what pressure of CO2 would be required to keep 0.12 molar, which is the molar solubility of soda in water in this case. And once again, we would use this equation, but we won't have to do this calculation, but just kind of show you what type of pressure we're looking at here. So we'll use this version of it. Thus the molar solubility is equal to K times P. So that's the molar solubility equals K times P. And this K value would be for, that's what's Henry's law constant, and that is this value here. Molar solubility is basically the molarity here of our soda. So if we solve for the pressure, it'd be S over K, which would give us 0.12 molar divided by 3.4 times 10 to the minus 2 molar per atmosphere. When you divide the bottom, the units flip and these guys cancel, leaves you with atmospheres as our pressure here. 0.12 divided by 3.4 to the minus 2. We'll call it like 3.53 atmospheres, right? Normal pressure is like 1 atmosphere, right? So you got over 3 times the pressure in that soda can, and that means that's going to keep all that CO2 dissolved in your liquid part, right? So much higher than normal pressure. Atmospheric pressure about 1, not in that ballpark. So you got about 3 times or so more pressure in that soda can, and that again is what's going to keep it fresh in a sense and allow the proper amount of CO2 to be present. So let's talk really about concentration units here and different ways that we express concentration units. Let's first talk about also how you make a solution. So this is one way that you can make a solution. And again, when we make a solution, we have our 2 parts, which is our solute. And again, that is the smaller part of the solution. That's usually the solid you dissolve in it. And the solvent, which is the larger part of the solution. And, you know, that is, you know, something like water, for example, the liquid or substance that you dissolve in it. So when we do this, you could take a little bit of what you want to dissolve into a flask like this. This is what's known as a volumetric flask. Volumetric usually means expensive, and you shouldn't break these things. Also usually means, by the way, there's just one line right about here, for example. And that one line is the actual volume that you're looking for. We use volumetric flasks. We typically go to 2 decimal places. So that would be something like 1.00 liters. So you put your solid in there, use a little funnel, add some water. And usually in this case, you would probably want to add water to about here, for example. And that will give you enough to kind of put the lid on it like you see here and give it a little mixy, maybe not so much shaky. And you want to continuously, again, probably continuously add more water and more mixing. You usually want to keep the sort of water layer out of the neck of the flask until you're ready. And you want to dissolve everything or get pretty much everything dissolved when everything's on the bottom there. Why do I need to continuously add more water, for example? That is because the solubility of whatever I'm dissolving may require more water to be added, right? That's like so many grams per 100 grams of water. We kind of keep adding enough water on the bottom part of this flask to get it completely dissolved. Once it's dissolved, we then can add water to the line, once again looking for our meniscus, right, our curvature to be right there at the line. We can put the cap on it, give it a good mix, and we will then have the solution at the proper concentration that we made. So that's a nice, very good way to make a solution, a very accurate way also to make a solution as well. So let's talk about some units here. The first type of unit we're going to talk about are percent units, and the first one is mass percent. And this is sometimes referred to as percent m/m, and that's mass to mass percent. And it is the mass of the solute divided by the mass of the solution times 100%. In this formula here, this is really the important part, because remember that the mass of the solution is both the grams of the solute and the grams of the solvent. And I can't tell you how many people in these type of problems will just divide by the mass of the solvent. And the reason that's so easy to do in these type of problems is a lot of times they will give you the mass of the solute and the mass of the solvent separate from each other. So a lot of times what people will do is they'll end up just dividing by the solvent and not adding them together to make sure that you actually get the mass of the solution. So make sure, especially in these type of problems, that you do that, because it, again, is a very common mistake that people make when they're trying to calculate these things by not sort of getting both parts of these. They end up just getting the solvent, but you do need that solute as well. And once again, they are sometimes given to you separate. A variation on this sort of formula is what is sometimes referred to as ppm, or parts per million, and that is the mass of the solute divided by the mass of the solution times basically a million, or 10 to the 6, right? That's 1 times 10 to the 6, which is a million. And sometimes parts per million is used. So if somebody says parts per million, it's basically this formula, except by multiplying by 100%, you multiply by a million and it turns into a unit. So sometimes those units are used a lot for certain things. So again, if you see parts per million, it's sort of this sort of deal. And you'll be multiplied by a million rather than 100. I'd say most of the time, though, probably in chemistry, that you're going to use that formula just like this, where we were looking for mass to mass percent, but sometimes parts per billion, parts per million, even parts per billion, by the way, also very commonly used kind of off of this formula. So let's take a look at this one here. So why don't you take a moment and see what you come up with. A solution is prepared by mixing 2.5 grams of calcium chloride with 50 grams of water. Calculate the mass percent of calcium chloride in this solution. So take a moment and see what you come up with here. Let's take a look. So let's identify a couple things. We've got 250 grams of calcium chloride dissolved in 50 grams of water. That looks like a smaller number, so that's going to be my solute. That looks like a larger number, so that's going to be my solvent here. So we have the mass of our solute, 2.5 grams. We have our mass of our solvent, 50 grams. And we're looking for the mass percent, which again is our mass of our solute divided by the mass of our solution times 100%. So That's our solute. That's our solvent. Remember, that is not 50. Is not the solution. It's just the solvent. So the mass of the solution, which we need, which is the bottom part, is the mass of the solute plus the mass of the solvent. That's going to give me 50 plus 2.50 grams. That's going to give me 52.5 grams of solution. So that is, again, the number we want to use, and not 50, which a lot of people will use. So now that we have the right number there, we're ready to go. Let's pop it in. Percent mass to mass, going to be 2.5 grams divided by 52.5 grams of solution times 100%. It's going to give us 2.5 divided by 52.5 times 100, not 1,000, but 100, 4.76. So this would be 4.76%. M/M is a good way to do that. And you could even put what it is, calcium chloride, right? Any questions on that one? Hopefully not. Again, most important, want to make sure that we use our actual solution, not just a solvent. All right, let's try another one here, see how we do. Let's do a concentrated hydrochloric acid solution. Contains 37.2% by mass hydrochloric acid. What mass of hydrochloric acid is contained in 35.5 grams of that concentrated hydrochloric acid solution? So take a few moments and see what you come up with on this one. All right, let's take a look and pull out some information. So clearly we have the mass percent given to us. And so we're going to be perhaps using this mass of our solute divided by the mass of our solution times 100%. Let's pull out our information here. So we are given the percent mass to mass in this case, which is 37.2% hydrochloric acid. We do have the mass of the solution, which is 35.5 grams, and we are looking for the mass of the solute. So how do I know I'm looking for the mass of the solute? Well, here's the deal. When you have sodium chloride solution, the solute is sodium chloride, the name of the solution. You have a hydrochloric acid solution. The solute is hydrogen chloride or hydrochloric acid. If you have a potassium chloride solution, the solute is the potassium chloride. So since we're looking for how much hydrogen chloride or hydrochloric acid we have, that is definitely why we're looking for the mass of the solute, and that's why that is the mass of the solution. Now, sometimes it's easier when you do have a percentage given to you to convert it into a conversion factor and do more of a dimensional analysis approach than maybe just plugging and chugging. You could just plug and chug, as you do have this and you do have this, which means you can solve for this. So you could definitely just plug and chug into there and you'll be okay. But if you want to take more of a dimensional analysis approach, and we do have something that's a percentage, remember that when you have something that's a percentage, if you assume 100 grams, you're in business. That's a good way to do it. So what would 37.2% hydrochloric acid mean? It would mean I have 37.2 grams of hydrochloric acid in 100 grams of solution. Or we could use it in the opposite way, 100 grams of solution, I would have 37.2 grams of HCl. So if we took more of a dimensional analysis approach, we have our 35.5 grams of our solution. We want to go opposite so it cancels. So there we go. That will do it for us. We're going to take 37.2 grams of HCl, 100 grams of solution. The grams of solution will cancel each other out. And we're going to do 35.5 times 37.2, a little divided by 100 action. And that's going to tell us that we got in there 13.2 grams of HCl. Now, could you have plugged and chugged into this equation? Absolutely. You would have had or you could have went this way, 37.2% equals my mass of HCl, which I'm looking for, divided by 35.5 grams of solution times 100%. So we would multiply the 35.5 to the other side, which is essentially what we did right here. So we would take 35.5%. We would times it by 35.5 grams. We would then divide it by 100 to this side. So divide and multiply. And we would have 100% in this case equals our mass of our HCl, which would equal the same thing. So if you want to plug and chug, it's really the exact same math as doing more of a dimensional analysis approach. And sometimes with these percent concentrations, kind of assuming 100 grams and turning them into a usable conversion factor, is sometimes really, really helpful. All right, let's talk about a few other percent compositions or percent concentration. This is volume percent, like in alcohol, percent by volume. And is the volume of the solute over the volume of the solution times 100. It's kind of milliliters over milliliters times 100%. This is one that you probably don't have to worry too much about. The bottom part, usually in these problems, they will give you the volume of the solution. So same thing, if you wanted to turn it into a usable conversion factor, if you had 4.25% volume to volume sodium chloride solution, what that would mean is if you turned it into a usable conversion factor, you would have 4.25 milliliters of sodium chloride in 100 milliliters of solution. Or again, you could flip it around and use it in the opposite direction as a conversion factor. 100 milliliters of solution, you would have 4.25 milliliters of sodium chloride. And again, that is a way you could just kind of make a more dimensional analysis approach if you wanted to, and use them as a conversion factor. In addition to that, the last sort of concentration type unit is mass to volume. And this is, as you can see here, sometimes referred to as percent mass to volume. It is the grams of solute over milliliters. So like grams over milliliters, kind of like density. Give times 100% in this case. Same idea. Once again, you probably don't have to worry too much about the bottom part here because most likely they'll give you the volume of the solution. If you did have, say, a 4.25% mass to volume of sodium chloride, that would mean that you would have 4.25 grams of sodium chloride in 100 milliliters of solution. Or in 100 milliliters of solution, you would have 4.25 grams of sodium chloride. So once again, might be easier in certain calculations to just sort of move them into a conversion factor and sort of do more of a dimensional analysis approach. All right, so percent mass to mass, percent mass to volume, and percent volume to volume are three common sort of concentration units that are used. So let's take a look at another example here. What is the mass to volume percent? Br2 in a solution prepared by dissolving 12 grams of Br2 in enough carbon tetrachloride to make 250 milliliters of solution. All right, we're looking at mass to volume. So percent mass to volume here means that we want the mass of our solute divided by the volume of our solution times 100%. In this case, I think we got everything we need here. That is our solute. And then that obviously is our solution, as it says. And they're actually in the right unit, so we're good to go. So we'll go with 12 divided by 250 milliliters times 100%. Going to give us here 12 divided by 250. I'm going to times by 100. Not forget to do that part. 4.8%. I would say most people will just get rid of these units here and leave it as 4.8% and put the M/V in this case. Now, this also question brings up a pretty good point about what we were talking about earlier. The solute here is Br2. This is actually the solvent, right? It is not water in this case. It is carbon tetrachloride. Why would water be a bad solvent in this case? Take a moment, think about that. All right, so hopefully in your screen there, you are saying water is a terrible solvent for Br2, and that is because Br2 is non-polar, right? Bond between bromine and bromine going to be non-polar, makes it a non-polar molecule, which means if I try to dissolve it in water, which is polar, we're going to get an not going to work, right? But if I take something like my carbon tetrachloride, which looks something like this, if I just quickly draw it without all the dots on the chlorines, that is a symmetrical geometry. Once again, that means that this is a non-polar molecule, which means when I take carbon tetrachloride and Br2, which are both non-polar, they're both going to be using dispersion forces, which means, unlike with water, we'll get a happy face on this one, it's going to work because that is like dissolves like. So they will both be using dispersion forces and no problem in this situation. So once again, tying together earlier, we talked about earlier in this chapter, like dissolves like, similar intermolecular forces. That is why in this example, water is not the solvent. As I might have said before in some previous lectures, water is a really good solvent for a lot of things that are ionic and polar. Terrible solvent for something that is non-polar because they're not going to mix together. All right, let's take a look at one more here to finish this sort of part out. Calculate the grams of KCl and the grams of water in 225 grams of a 8% mass-to-mass solution of potassium chloride. All right, let's take a look here. So obviously we got some mass percent. So once again, we do have our formula. Our mass of our solute, or mass of our solution times 100%. In this case, we're looking for the grams of KCl in a KCl solution. Remember, the name of the solution is our solute. All right, so we're definitely looking for this guy. And we're looking at how many grams of water, which would be our solvent. And once again, we do 225 grams of this solution. So we do have this, and we do have the percentage. So we can plug and chug into this equation, solve for the mass of the solute. I am again going to take more of a dimensional analysis approach rather than just plugging and chugging into here. So this 8% mass to mass means, once again, that I have basically 8 grams of KCl and 100 grams of solution. Once again, I can flip it around and go 100 grams of solution. I would have 8 grams of KCl. And I do have 225 grams of the solution. So I do have the mass of the solution, which is 225 grams. So I'm going to do this again as more of a dimensional analysis. So I'm going to want to get rid of my solution. So we're going to use it like this. And again, here we'll have our 8 grams of KCl and 100 grams of solution. That again is the same thing if you rearrange this equation and solve for the mass of the solute. The mass of our solute would equal our percent mass to mass times our mass of our solution divided by 100%. So basically that is the mass of the solution. That is our 8 grams, which is basically our percent. And on the bottom is our 100%. So it's, again, basically the same math there. So if we do this, we will get 225 times 8 divided by 100. Going to go with 18 grams of KCl. That is the amount of solute that we would have. We're also looking for, in this case, how much water would we have? So in honor of water, we'll go with blue. So we do know that the mass of the solution should be the mass of the solute plus the mass of our solvent. So remember, in this case, this is the KCl. The water is our solvent, and obviously that's the mass of our solution. So we know from the problem that we had 225 grams as the mass of the solution. We just calculated how many grams of KCl was in there, plus our mass of water, which is our solvent. We're going to subtract 18 to the other side. And that will get us 225 minus 18, about 207 grams. 207 grams of water here in this particular case. So this solution is basically made out of 18 grams of KCl dissolved in 207 grams of water. When it's all dissolved together, we end up with a total mass of that solution of 2.25, not 2.25, but 225 grams. And it does have 8% as a sort of concentration unit. So in this case, we think about our solvent and solute just to tie together what we talked about at the beginning of the chapter here. In this case, we have something that is ionic, dissolved in something that is polar. So once again, that's going to work well because it could do that ion dipole where when we put our Ka plus in the solution and our Cl minus in the solution, the water is going to have no problem surrounding these guys and dissolving, as we talked about earlier in this chapter. So once again, water oftentimes really good solvents, used a lot for ionic and polar things. But once, as we saw in the previous example, not the greatest choice there for non-polar things. All right, I think at this point we will wrap it up here as to not go longer here. I know it's going to go a little bit longer here with the next topic. So good stopping place. We're going to stop here for part 1 of chapter 14. We will return for part 2 shortly, and we will talk about molarity, which is probably the most common unit of concentration. We'll also talk about dilution, and we'll get to that stoichiometry that involves solutions, and perhaps some ending with some properties of solutions. So again, not to make this one too long, so hopefully when it's all said and done, it won't be as long as it would be if we continued. We'll see you for part 2. This concludes part 1. Have a good one. See you in part 2 shortly. Have one nice one. Bye-bye.
Hello and welcome here to the end of part 1 of our lecture here on solutions. Let us finish it out like we like to do with a joke. What is Avogadro's favorite sport? Yes, it must be golf. He always got a mole in one.